This is a recording for section 14.4, the last section for graph theory. It's called trees. A tree is a graph that is connected and has no circuits. All trees have the following properties. There is one and only one path joining any two vertices. Every edge is a bridge, and we mentioned that a bridge is an edge that if it's removed, the graph becomes disconnected. So the following are trees because they don't have any circuits and they are connected graph. It says list the number of vertices and edges in the trees. So let's look at the number of vertices and the number of edges for each example. All right, so let's look at the first one, and as you can see, they're actually even numbered. 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. That there are 6 vertices, and if you count the number of edges, 1, 2, 3, 4, 5, there are 5 edges. Again, it's a tree because there's no circuits, and it is connected. Number 2 here, you can see that the vertices are also labeled, so there's a total of 25 vertices. And if you count the edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 edges. And for question 3, there are 1, 2, 3, 4, 5, 6, 7 vertices. And 1, 2, 3, 4, 5, 6 edges. So it says, can you guess how many edges in a tree with n vertices? So let's look. If there was 4 vertices, there were 5 edges. 7 vertices, 6 edges. 25 vertices and 24 edges. So if you want to pause this and try to figure out the answer and then see if you get it correct, I would recommend doing that. But if you notice that if there are, each time the number of edges is 1 less than the number of vertices. So if there are n vertices, there are n minus 1 edges. And that is the property for any graph that is a tree. For any tree, if there's 10 vertices, 9 edges. 100 vertices, 99 edges. Why are the following graphs trees? Why or why not? For part A, this is no because it's not connected. It has to be connected to be a tree. Part B is yes, it's connected and has no circuits. All right, and we learned all about what circuits were in the last section. And is this one a tree? No, here is a circuit. Trees do not have circuits. So for the tree above, verify that there are if there are n vertices or n minus 1 edges. So for part B, that was the only one that was a tree. That was the only one yes. So 1, 2, 3, 4, 5 vertices for part B. And so we know that there should be 4 edges, and there's 1, 2, 3, 4 edges. So that checks. So for any connected graph, you can decide if it's a tree also by counting the number of vertices and edges. So subgraphs or spanning trees, a subgraph is a set of vertices and edges chosen from among those from the original graph. So if you have an original graph like this, These are two possible subgraphs. A subgraph contains all the original vertices. Notice that both of those two graphs over here contain all the original vertices, but their edges are a subset of the edges already there, right? Like this one labeled number 1 is missing this edge, and the one labeled number 2 is missing this edge. So, but they only have edges that are on the original graph. A subgraph that contains all the connected graph's vertices and contains no circuits is called a spanning tree. So these ones I have labeled here, 1 and 2, are actually spanning trees. The original graph is not a tree because there's a circuit, right? But these two are spanning trees. They contain no vertices and they are connected. So example, find a spanning tree. And recall that a tree with n vertices has n minus 1 edges. So if you want to count originally that there are 1, 2, 3, 4, 5, 6, 7, 8 edges, or 8 vertices. So there should be 7 edges in the spanning tree. Okay, right now it's clearly not a tree because there's many cycles in this graph, right? But let's find one. So a spanning tree has to have all the vertices. So let's go ahead and put those in. A, E, F, B, H, D, G, C. So the spanning tree has to have all those vertices, and then we need to connect them with edges that already exist. Like I'm not going to connect from B to D because in my graph up here there's not an edge from B to D. So we want to connect this with the edges that already exist and create no circuits. So we can do something like this. And then it's connected and there are no circuits, and you can check that there's 1, 2, 3, 4, 5, 6, 7 edges, which is what we decided up here. There were 8 vertices, so there should have been 7 edges. So that is one spanning tree, but again, that there are many possible answers. So find 2 different spanning trees and find their weights. So these vertices aren't labeled, so I'm just going to put them in the pattern that they are in. So we can see again, this is that same shape as that first graph, that there is a circuit here. So we want to take from the edges that are already there. Here's one possible spanning tree. Contains no circuits. So it says find 2 spanning trees and their weights. All right, so let's go ahead and find the weight. And that is 119. And then let's draw a different one with the same vertices, but a different shape. So maybe we want to go here, 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 here. Again, it has to be edges that already exist on the original graph, and all of those do. 35, 17, 12, 15, 8, and 20. Add those guys up. And you get 107. Again, many possible answers for that one. So again, what we are going to be interested in is the tree with the least weight. So this time we're going to be interested in a tree, which would be like if we wanted to lay cable among houses so that everybody was connected, but we don't want to, right? This cable costs money, so, and we don't need any circuits, right? So we would look at something finding the least weight, right? The least amount of cable that we need. So, and that's what's in this question is this cable. The minimal spanning tree is the MST for a weighted graph. It's a spanning tree with the smallest possible total weight. So this one is about this. Telephone companies provided telephone cable and internet to the 7 small mining towns, right? And so we want to, figure out, over here it has a weighted graph of that same picture, right? Which in this it could represent the cost in millions of laying the cable. So we want to find the minimal spanning tree, the least amount of cable that we would have to use. So we have an algorithm that we do this that will guarantee the minimal cost circuit. It's called, or minimal cost tree is called Kruskals algorithm. It's very similar to that best edge algorithm, which is also called the cheapest link algorithm, but that one was to find a Hamilton circuit. So Kruskals algorithm is going to be the same kind of idea. We're just going to pick the edges with the smallest weight and keep picking them, but we want to create a tree. So if you think about a tree, you can have three edges out of a vertex for a tree. So you don't have to worry about that like you did with the circuit. With the circuit, we could only have 2 edges coming out. We made sure we didn't close the circuit up too early. With Kruskals algorithm, you can have more than 2 edges coming out because it's a tree, not a circuit, but you cannot create any circuits at all. So you want to keep picking until you are connected the graph minimally. Again, if you want to figure out how many edges you have to pick based on the number of vertices, you can do that too. If you have 4 vertices, there's supposed to be 3 edges that you pick, right? Or I hope you can look at it and just decide, okay, I'm done, it's a tree. So let's see how that works. 7 buildings on a college are connected by the sidewalk shown in the figure on the next slide. The weighted graph represents the buildings as vertices and the sidewalks as edges and the sidewalk lengths as weight. A heavy snow has fallen and the campus needs to be cleared quickly. Campus decides to clear as little as possible and still ensure that students walk from building to building will be able to do so along cleared paths. Determine the shortest series of sidewalks to clear. What will the total length of the sidewalks that need to be cleared? What is the total length of the sidewalk? So here there's a picture of the sidewalks and their lengths, right? And then we write it as redraw it as a weighted graph. And we are going to use Kruskals algorithm. And if you want to, again, you can list the cheapest weights off to the side. 242. 249 to make sure that you have them all. Oops, there's 245. So I'm going to put 245 in there, and I'm going to put 249. Those are all the 240s. Then there's 251. There's 2 of those. 253. 255, 256, 259, 262, 264, and 274. You can see that. So we've put them all in order. And again, you don't have to do that, but it helps people. So we want to grab the cheapest link, which is 242. So we're going to take that one first. If you want to circle it, you can. All right. 245, yep, that's fine. Remember, the only thing you have to worry about for a tree is that you don't create a circuit. That's the only thing you have to worry about. Again, we're wanting the minimal spanning tree. 249, yep, that's fine too. I haven't made a circuit. 251, yep, that's fine too. 251, I don't want this 251, right? Because this one makes a circuit. It would make a circuit between BA and D, right? It would look like this. But we don't want that. But we're still not completely connected because C and E are not connected to our graph yet. 253, yep. 255, no, that would make a circuit. 256, no, that would make a circuit. So that's no good either. 259, yes. And now you can see that they are all connected, and that is the minimal spanning tree. And again, if you wanted to start out and say 1, 2, A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, that there's 6 vertices, you know that you would be done when there were 5, 1, 2, 3, 4, wait, or there's 7 vertices, sorry. A, B, C, D, E, F, G. A, B, C, D, E, F, G. 7 vertices, and that there are 6 edges. 1, 2, 3, 4, 5, 6. So you know there's six edges, and you know then you would stop after that, right? And so if you look back at the question, it says determine the shortest series of sidewalks. What is the total length? So the total length, got to add all these up. 242, 245. I'm going to just looking at the top at the ones I circled. But I didn't circle that last one. 249, 251, 253, 259. Let's add up those. 242 plus 245, 249, 251, 3, 259. 1,499, and then put units on there. That was feet. 1,499 feet of sidewalks. All right, we will do one more example of Kresgel's. Find the minimal spanning tree. Which edge is chosen fourth? So again, you can put the edges in order, or you can just highlight it. Again, get your highlighter. So we'll choose that one first. Because over here it says which edge is chosen fourth. This is also 1, so it doesn't matter which one of those you chose first. 1, 1, then 2. I'm just going to go until I connect, and I make sure I don't put any, I don't make any circuits. This one would be chosen third. And again, if it helps you to write out them and like this, do so. So 1, 1, 2, there's no 3s. It looks like a 4, and that one's okay because that's not going to make a circuit. And then we have 5s. I don't want this 5 because this one makes a circuit. but I can, oh wait, there's another 4 up here. I would grab that first. See, there's a reason right there why you put them in order to start with. So we would choose this 5th. And we're not quite connected because G's not connected. But the 5 makes a circuit, this 5 makes a circuit, this 5 makes a circuit. And so the next cheapest is 6, and then you're done because you can see all the vertices are connected. So you would choose this one 6. And again, 1, 2, 3, 4, 5, 6, 7 vertices, so you knew there was going to be 6 edges. And it says which edge is chosen 4th, and that's this edge, which is edge CF. All right. So if you wanted to, you could redraw your spanning tree, and it would look like this. Your minimal spanning tree. Just redrawing it with the edges that I have highlighted. All right, that is the end of the graph theory, end of section 14.4.